keen and is very keen and motivated to foster connection between different companies to therefore ensure more circular economy around. So contact between different agencies, companies, and it's somewhat similar what we try to do here. So connect people to get a better outcome regarding the circular economy. And therefore, thank you very much, Dr. Schöps, for having you here. And now you can present your keynote, please.
Okay, thank you, Philip. Shall I take the screen back?
Yes, please.
No. Okay, can you see it?
Yes.
Okay. Yes, thank you very much for having the possibility to talk to you. I must apologize that my English is not so fluent. Sometimes I'm looking for words, so don't be disappointed if there is sometimes a break for looking for words. Anyway, I would like to draw your attention to Rewimet. At first, let me give you a short, brief view on what Rewimet members are and what the activities are. Rewimet consists of some enterprises from the recycling industry. You see here on the left-hand side and on the right-hand side the enterprises. Some of you, I'm sure everybody knows them, like Hilti, which is not a recycler, but a large enterprise, OEM, which is very ambitious in sustainable development of products and production. And some enterprises which are producing mainly metals, but also other materials from waste, like HC, Stark, like Taniobis, RHM, and so on. And on the bottom line, you see the communities, authorities, and on the headline you see the research entities like University of Magdeburg, TU Clausthal, and TU Braunschweig, and so on. And these are almost 30 members which are gathering in this community of Rewimet. What are we doing? We are doing research in the field of metal recycling. This is our main topic. And this has to do with networking. As you see, we have not only industry, but also authorities and research institutions. And the networking is my main task in this field. We are promoting young talents. You all know that this is a very ambitious target in Europe. In each industrialized country, young talents are rare, and we have to do a lot to get them in this, to get them interested in this field. We are advising policy, and yes, this all is for the increase of added value in metal production. So that's all about Rewimet. Let's step in. What are the mega trends which are influencing our economy? I would like to draw your attention on some of these mega trends. 1990, when I was 30 years old, we had about 5 billion inhabitants in the world. 30 years later, we have almost 8 billion inhabitants, and it is estimated that we will have another 30 years later, almost 10 billion people in the world. What does this mean? This means that the consumption of raw materials, energy, water, and land is increasing, and it is increasing rapidly. This is very important. Another aspect is that the consumption of raw materials is counted per capita, is very different. We have, this is not surprising, the most consumption in the USA, and but also Europe is somewhat in a high level of consumption of raw materials. And the fast-growing continents like Asia and Africa, they have rather little consumption of raw materials per capita. And this is another important aspect, that not only the number of people in the world is growing, but also if all these growing number of people want to consume as much raw materials as we do in Europe or they do in USA, this would be an incredible demand on raw materials and would be not sustainable for our planet. Another aspect, in our economy, we have not only shortages in raw materials, but we have as well sinks for waste. And these sinks for waste are becoming scarcer. Everybody knows about ocean plastics, and this is really a large problem. And this is caused mainly by developing countries in Africa and Asia. And we can estimate that every minute a truckload of plastic waste is dumped into the sea. And in some decades, if we keep doing this, there will be more plastic waste in the oceans than fish. This is really a large problem. We must stop it as quick as possible. The third point is global warming. Global warming is caused mainly by CO2 and other greenhouse gases. We have calculated from the beginning of industrialization, about 1 degree of Celsius, and in order to limit this heating to 2 degrees Celsius, I don't think that it is possible to go under this 2 degrees. Then we have to decarbonize, or to be precise, more or less to defossilize our economy. And this, for this, we need a turnaround in the production of our economy. So this is the third megatrend. Another megatrend is globalization. This is not really new. Globalization is an old thing. And if you, for instance, look at a rather simple product as a pair of jeans, and you can follow the line what the material is going, and you can count up to 50,000 kilometers what is which has the raw material traveled until it is coming to the consumer. And if you compare this with electronics, I think this 50,000 kilometers will not be enough. It will be much more. So globalization, of course, opens up markets. This is a great advantage. That is a driver for the international economy, but at the same time, their dependencies occur. This is another problem. This is two sides of the same coin. Next is worldwide logistics. If you look at such a container vessel, you see that they can carry about 20,000 or more sea containers. And if you unload this vessel, you get a line of trucks, 10,000 trucks, which is 160 kilometers long. Incredible what amounts of material we are shipping all over the world. And because this is a very large economy of scales, the transport is rather cheap, and the energy consumption, the CO2 emission, is not calculated, and because of that, it is cheap, and everything works. And this is a rather new that it sometimes does not work. And you all know this event in the Suez Channel. Sometimes some things goes wrong, and in this case, the freights for this container shipment goes up to the heaven, and because of that, we should think about whether this is the right way to go our logistics. Well, what does the European Commission do? The European Commission has developed the Green Deal. You know this all 2 years ago almost, and going further on to the Circular Economy Action Plan from July this year, there was Agenda Fit for 55. And what does this mean for the production? I'm looking now for the for your topics, and I saw 2 topics. One is the CO2 price. CO2 emissions will be more expensive. The trading system will be limited, and it will be replaced by a tax system, and this tax will be cashed out not only within the European Union, but also there will be a border adjustment, so that the CO2 backpacks which products from abroad bring in will be cashed on the outside border of the European Union. In my opinion, this is necessary. Otherwise, it would be impossible to have a green production, for instance, for steel, if cheaper products from abroad come without paying for the CO2. It is necessary to create a level playing field. Okay, let's go on. What are the fields of action for the circular economy? Yeah, we have to look for environmental education. We have to look for material flow forecasts. We have to calculate what material can we get at this at which place. When we look at the field where consumers use products, we must look to what we can get from the consumers. What have we do? How can we reach consumers to bring back their products? This has to do with behavioral economics, with psychology. Then we need, of course, simply collection systems and treatment processes. Of course, this is our main topic where we are working on treatment processes to develop proper technologies for that. Then more and more it is necessary for cross-company networks, because recycling process is not only one step, it is always large chains of steps, and there you need cross-company networks. Very important competition is of course a main thing which has to be considered in a free economy, of course. And then we have to look what is the main hindering for the use of recycled materials. Often it is difficult to bring recycled materials in the raw material economy back. And also it is difficult to construct recycling facilities, because we have risk of fire, of noise, of smells, and so on, and dust, which is connected with the recycling processes. Well, what helps? It helps to look for best practices, for examples, to build model regions, to have a common understanding for the needs what we have. Then, of course, efficiency and sufficiency. I'm sure that we have a lot of potential not used up to now in regard of efficiency. And the other side is the question, what do we really need? Do we really need everything what we are doing? And topic of which is influencing all of this, what I have said in this fields of action, is digitalization. This is a powerful tool for improving the processes. And what are we doing? For what are we doing this all? For the principle cradle to cradle. That is what we need to implement in our economy, in my point of view. And for me, just the small thesis, imagine there's just no dump site. And to give a help for how can we indeed use this, what can help to have imagination. How can we can we realize this? Is the metal wheel? This is from Markus Reuter from Freiberg, and you see here that these colored dots are in these sectors. Here is a sector for copper and nickel. Here is a sector for zinc and lead. We have sectors for other metals. These are base metals for the industry. And green dots mean that these metals can be recovered on the route of copper and nickel, for instance. A yellow dot means that it can be recovered, but it's difficult. And the red dot means that it is impossible to recover these red-colored metals in the route of the production of nickel and copper. And here, for instance, you see that there are a lot of green dots, and as well there are a lot of green dots in zinc and lead. And this means that on this route of the non-ferrous metals, zinc, lead, copper, nickel, a lot of metals can be recovered. Not so in the sector of iron aluminium. There you see no green dots. It is very hard to get the recovery of metals in the route of iron production or aluminium production. It is almost impossible to get metals back. So for your ambitious project, I would like to draw your attention to this sheet, which means that it is no problem to mix, for instance, materials which contain copper and precious metals, or copper and zinc, or copper and lead, and so on. This is no problem because these metals can be separated in the copper production by recycling processes. It's not a good idea to mix iron with copper or aluminium with copper. This is shown by this graphic, and this is what I would like to show you as an example for what is good for recycling processes and what is harmful for recycling processes. Yes, that's all what I would like to bring to you in this keynote. Thank you very much for your attention.
Well, thank you very much for the interesting presentation. Now for the questions. If there are any questions, please either write it in the chat if you're not willing to tell them. Otherwise, you can also activate your microphone and ask the question directly.
Well, maybe I have one question about the metal recycling. Well, I guess this graph is more focused on if we want to extract exact alloying elements from the smelt, but then how about then recycling the end material as is, kind of bringing it back, for example, stainless steels from an end product and take them back to the beginning of the cycle.
Sorry, I didn't understand the question.
So I think this graph is about if you have, for example, a copper-based or nickel-based metal which has some alloying elements in it.
Yeah.
Then from that one, it's easier to kind of regather the alloying elements. But maybe my question is that only about the end products and recovering the same material from the end products as the.
I think I got it. Of course, it's no problem when you have an alloy which is just used for the same purpose again. Then it's no problem to have a ferrous alloy, iron-based, for instance, with chromium and nickel and so on. Then it's no problem, of course, to melt it and use it as an alloy again. But it's hard to separate the metals if you would like to do this. This is it's rather hard.
And I guess in that case, it's only dependent on the kind of melting temperature of the metal itself.
Yeah. We have some cases where metals even can be recovered from the slag of the melting process. For instance, when you look at the tin process, then you can see that tantalum oxide has a red dot. This means that tantalum can be not obtained from the tin smelter, but the contents of tantalum in tin slags are sometimes very high, up to 1.5 or 2% tantalum in the tin slag, that the tin slag itself can be used as an input material for the tantalum recovery. And the same is already developed for the treatment of batteries, lithium batteries. When you bring them into the copper process, like here, you can easily obtain copper and nickel and cobalt. Cobalt is here, nickel is here, there's no problem. The problem is the lithium. Lithium is not marked here, it's not inside, but if you melt only the batteries and do not mix this with other copper scraps in a large smelting oven, then you can obtain a slag from which you can recover the lithium. This is possible.
Yeah, thanks. Maybe another question about the cluster itself. How are the companies collaborating? Are they providing each other with scrap metals to recycle the elements, or how does it work?
Yes, this is really often the case. The waste of the first is the raw material of the second. Sometimes it works like this, yes. But not only. They are very different in their processes, in their material streams. We have one processing electronic waste, complete appliances. We have another one which treats only the printed circuit boards which are extracted from the appliances. We have an enterprise which is the largest tungsten recycler in the world. We have tantalum recyclers. We have the largest aluminium recycling plant in the world from Novelis, which is melting about 400 tons aluminium cans per year, and so on and so on. It's very, very different.
Okay, thanks.
I also have a question, maybe like, how do you go about the recycling of precious metals, which are now very often combined with plastics, because we see now they're experimenting with 3D printing antennas, all that. So a lot of precious fiber metals are getting mixed up with, not with other metals, but with plastics or even with smart textiles. Is that, do we have an answer to that challenge already, or?
Yes, I do. It's for us not good that precious metals are more and more dissipated in our products. And up to now, it is, let's say, not a large problem to get back the precious metals, for instance, from printed circuit boards or from smartphones and so on. This is not really a problem. It will become a problem when, for instance, the content of gold goes below 10 grams per ton, because this is the limit deduction which the smelters have. This 10 grams per ton is that content which they cannot get out of the waste. And if sometimes you have clothes or other products where let's say RFID chips with small amounts of metal, silver or gold or so on, and this is dissipated in that way, then it will be a problem. It is not a problem when you have, let's say, a smartphone, then the plastic content, or a circuit board, then the plastic content is helpful for the smelter because this delivers the energy for the process. So it's good not to separate plastics and precious metals, but instead of that, bring the mixture to the smelter, and then the copper is collecting all the precious metals, the plastics bring the energy for the process, and the inorganic materials like glass fibers and ceramics are building a slag for the copper process.
Okay, yeah, but so for example, it would be interesting if we enclose, they have a lot of RFID tags. I would presume, speaking as a designer, that clothing manufacturers would maybe redesign their tags in a certain way that they can be separated from the clothing, and then a big bag of RFID tags is more interesting to recycle than RFID tags in a bunch of clothing.
Of course, but larger concentration is always better than dissipation.
Yeah, okay, thank you.
Okay, I think we have time for one short last question. Somebody has a small question.
We don't have to force this.
Okay, yeah, I see. So well, I think, yeah, anyway, we hit the time mark for that, I think. Thank you very much for the interesting presentation. Also, the variety of aspects you talked about networking, the CO2 footprints, also the problem of, yeah, more and more plastics are swimming in the oceans, and the effects on the global climate, and also the logistics. So you had a lot of different aspects, which also all has to be tackled, not only separately, but in combination of different people who are keen to solve problems. So thank you very much. And well, then I think I gave the word to Yannick now.
For me, it's time to leave. Thank you very much for the opportunity. It was a pleasure for me, and I wish you all the best for your projects. And I say goodbye. Thank you very much.
Thank you. See you next time.
Okay. Thank you very much for the presentation. So maybe briefly, before we go on to the next keynote of Hyperion Robotics, I would like to promote a little bit another program which will take place in November and December on the circular economy, specifically targeting PhDs. So this is another program which is also supported by the EIT RawMaterials and its EIT RawMaterials Academy. So just wanted to take a minute to talk about this, and I'll now give the words to Thomas, who will introduce Hyperion Robotics.
Yeah, thanks, Yannick. So I will be brief and let our guests do the talking themselves, but briefly, Ashish Mohite is the co-founder and CTO of Hyperion Robotics, a company which was founded in 2019. We also have Fernando de los Rios present. He's the CEO of the company. And Hyperion Robotics is doing extrusion-based 3D printing of concrete and trying to disrupt the construction industry this way. And they are attempting to make the process more efficient and also more sustainable. But I will let Ashish now take the floor, and he can explain better himself. So please, Ashish.
Do you see my screen?
Yep.
Okay, the presentation screen, right? Okay. All right. Thank you, Thomas, for introduction, and thank you for inviting me for this event. I would take this opportunity also to give a little bit of background of who I am, because it's important to know always who I am, what I am doing, and why I'm doing this. So as Thomas also introduced before, so my name is Ashish. I'm an architect, and next week actually I have my doctoral defense, so I will be finished with my PhD. And I'm passionate about how technology can influence the way we build, because I'm an architect. I'm also co-founder and CTO of Hyperion Robotics. So as I said, I have a bachelor's in architecture from India and master's in architecture from Germany. And for past decade, I have been doing research in 3D printing in AdLab, which is Aalto University's digital design laboratory, where Thomas is one of my colleagues. And I have used almost every 3D printing technology in the world. And I have also abused every 3D printing technology in the world and all different type of materials which can be used in the printers, which they are not supposed to be used. Just to give you some examples, so I have used SLS printer. So we have a homemade SLS printers in the lab, and one day I decided let's put some sugar in it. So we 3D printed sugar by melting the sugar by laser, and then actually use that sugar as a mold for casting metal and plastic silicon, for casting silicon with lost cast method. I have also been working with another project where we have been creating this kind of reindeer bone china, so new type of ceramic material, but using reindeer bones, which is a bit of a problem, environmental problem in northern Finland, and also using SLA technology to actually use that and print with that. I have also done WAM, so wire additive manufacturing, so 3D printing by welding. So this is also part of my PhD research, and I have also been teaching in Aalto, and this is some of the student work where they have been using food printer to print food and then afterwards grow mold on it. So this was just to give you an example of what I was talking about of abusing the 3D printers or using them in a way that they are not meant to be used. And this is the title of my PhD, so speed-based additive manufacturing technique, discovery and exploration of design potential of speed of deposition in additive manufacturing. So I have created a new novel way of additive manufacturing by changing the speed of the printer, and also asking a main question, which is also very relevant to this topic, because the question is can machine produce craft? So this is a question which is there in my PhD. The PDF is already available online, so you can read it. And if you have time, well, you do not have time next week because it's the final presentation of your hackathon, my PhD defense at the same time. So why AM in construction? As you know that the construction is also, it's one of the largest industry in the world, but you might not know that it's the least automated industry out of all the industries. And that leads to insufficiencies, that leads to waste of material, waste of time and resources. And the biggest culprit is also that this is very highly polluting industry. Only cement is responsible 8% of the CO2 production in the world, and concrete is actually the most used material on the planet after water. In the European Union, 20% of the energy is just used for cement production. And just to the simple answer would be like, let's stop using concrete, but that's not a possibility because concrete is not going anywhere. As you know that the world, this is the second most used material, so it's not going to change that. And world has more and more appetite for concrete, so we are using more concrete than we were using before. Just an example, China in last decade has used more concrete than the entire world combined in the last century. And now countries like India are building a lot of infrastructure. There are like almost 1,000 metro stations under construction in India, and all the metro lines are elevated, which are built in concrete. So just to put it shortly, that concrete is really not going anywhere. So what is the solution? How can we make construction sustainable and reduce the CO2 footprint by doing sustainable construction? And what I believe and what we believe at Hyperion is one of the solutions would be by using automation and additive manufacturing. And what do I mean by sustainable material is using end of life cycle materials. So we are striving at Hyperion to create this kind of construction which is sustainable, but at the same time using end of life cycle materials. So what do I mean by end of life cycle materials? So world has a lot of garbage. We consume a lot, but at the same time we create a lot of garbage by production of this raw material. Mining industry itself produces 223 billion tons of waste, and only 8% of that is getting reused. So this is a potential raw material which can be used. Just another example, in Finland, for example, like 96 million tons is the mining waste is existing in this kind of large pits. This is an example from a picture of a mine in Finland. Then you talk about other industries like paper industry, for example. So paper industry produces 240,000 tons a year in Finland. And we talk about iron industry. So like there are materials from the iron industry which also can be reused. So iron industry produces almost 2 billion tons of slag, which was also mentioned in the previous presentation. But slag is also an amazing material which can be used as a replacement material for cement. So all these materials which I'm talking about are the materials which can be used as replacement for cement. And then there are other materials like silica fume, recycled glass, biochar. All these materials can be actually replaced, can be partially replaced to replace cement, can be partially used. And this way we can actually reduce the carbon footprint of our construction. So now this is just, again, was an introduction of why we do what we do. And now I will talk about what we exactly do. So what do we do at Hyperion? So at Hyperion, we are 3D printing reinforced recycled concrete. So we are trying to reduce the footprint of concrete, the CO2 footprint of the concrete by using end of life cycle materials. And by doing that, what do we achieve? We can actually create a construction or buildings or our environment sustainable, faster, cheaper, and safer. And then from now on, I'll go through some case studies of the current projects which we have. So you actually know like what it means in practice, because how does it work in practice? How does it work in the global scale? How does it work with actual companies? So the first example is, as I was mentioning, paper industry waste. So paper industry produces 240,000 tons of waste every year, and then it just goes into landfill. So we are working with one of the largest paper manufacturer and wood manufacturer in the world, and we are trying to use the waste product, the waste paper sludge, which then cannot be recycled anymore, as a replacement material for cement. We are also using bottom ash from their kilns. So paper also, when paper is produced, there is kiln and there is bottom ash which is created. So we are also using that as a replacement material. So with that, we have been actually able to achieve a concrete mix, which is 90% recycled. So 90% of that concrete mix, all the raw materials are coming from end of life cycle. So if we were not using those materials, they will end up in landfills. So this is one example. Why wood manufacturing companies interested in concrete, you will ask, but the answer here is very simple, because when you talk about this wooden skyscrapers and let's build by wood and all this talk which is going around, at least in Northern Europe, but what people forget to mention or forget to understand that is that the wooden buildings have more concrete than wood, right? So what about that concrete which is all behind in the columns, in the slabs, underground? So that's why the wood company is interested to create this kind of new bioconcrete using their own waste products which they produce in their paper mills. Another example, a case study too, is we are working with a mining industry company here also in Finland, which makes machinery for mining industry and also does like recycling of mining waste. So with them, what we're trying to create is like a new geopolymer mix. So in this case, geopolymer is a different type of, I would not call it concrete, but it's a different type of mortar, which is a replacement for cement-based mortar. There is a different kind of chemical reaction. But what we're trying to do here, we are trying to use the mining tailings, which is the waste material from mining, which is, we have billions of tons around the whole earth. So what we're trying to do here is to take that mining tailing, the mining waste, and trying to create a new mix of material, which then can also replace cement-based concrete or cement-based mortar. And with that, we are trying to print this kind of silos, which then will be used to recycle more material. So this is the second example. So all these examples are real examples and real projects which we are currently undertaking. The third example is Iberdrola. So Iberdrola is a Spanish Fortune 500 company which is into renewable energy sector, and they build wind farms around the world and energy distribution networks around the world. But they also have a lot of concrete which goes underneath these pylons, for example, which is in the picture. So they had a startup challenge to figure it out how new companies could come up with new ideas to make their processes more sustainable. So we came up with an idea for them, is an example of a foundation. So everything, every building, every bridge, every structure needs a foundation. And right now, how the foundations are made is this like monolithic concrete block, a cube, where concrete is poured. So we came up with a solution using design for additive manufacturing, because in additive manufacturing, you only add material where it's needed, right? So you can actually reduce the amount of material. Most of the concrete used in our structures is designed to take its own weight because concrete is heavy. So by reducing the amount of material which is used by additive manufacturing, we can actually reduce 70% of the material used by them in a foundation. So what does that mean? First of all, it means that you need lesser volume to fill in. So you need to dig less. You need lesser volume of material to be carried to the site. So in all, they can actually reduce their carbon footprint of building this kind of foundations around the world by 70% to 80%. The third example, so the fourth example is marine infrastructure. As we all aware of global warming and sea level rising, the heating of our seas and destructions of destructions of reef structures around the world. So our proposal for that is to create artificial reefs So this is an example of artificial reef, which we 3D printed using the waste material from paper pulp mill. And this artificial reef right now is underwater in the Baltic Sea in Rostock. So this was a project we did for Fraunhofer Institute in Germany. And this is the result after 1 month. So after 1 month, you can already see that there is already a lot of sea life which is growing on top of it. And it's creating like a home for fishes. Our idea here is also to create this kind of underwater reef structures, which then could protect our coastal shoreline. So the waves are not getting really high. So they can dissipate the waves which are coming on the shore. They can also create fish habitats, and they can also create a colony for fish to grow and lay eggs and have a happy life. So these were some examples of current projects which we are undertaking. The question also we get asked all the time is like, why now? Why do you think it is the right time? What we believe is that every time there is a new technology, so when we're talking about additive manufacturing, we have a chance to use actually the new materials, right? Because we have a new technology, so why not use also new materials? If you have the new technology, there is an opportunity, and we think that it would be a missed opportunity by using a new technology but using a really old material. So what we believe is that right now is the right time to change the way we use concrete, change the way we produce cement, change the way we actually use our resources. And at the same time, with the benefit of additive manufacturing, you can also reduce the amount of material which can be used. Also from previous presentation and your information, you know that EU has a new target for CO2 emission. So the legislation is also moving towards using less materials, using recycled materials, using carbon sequesters materials like biochar to create this kind of a new infrastructure. And this is the right time to do it. That's why this is the right time to do it. How do we do it? So we are a B2B business. So we, as the previous examples, is that we work with businesses. So we work with other companies. So for example, the wood manufacturer or the mining machinery manufacturer or the energy distribution company, and we create new solutions for them. How do they create concrete, or how they build structures, how they build infrastructures, and create a new sustainable solution for them by using actually waste material from them. And we give them this kind of product as a service. So this is something which we sell to them, and this is something which we work with them. How does it work in practice is that we sell them a robotic 3D printing system, which is automated, which automates the construction. So there is a hardware, there is a software component to it. And then we also provide them how they can use the circular materials within their own portfolio or what is available locally to create this kind of a new concrete or new mortar, new sustainable way of building. This is very important because our customers around the world, and around the world there is different availability of the materials. So we have customers in Mexico, we have customers in Argentina, and we have customers in Finland. And everywhere the availability of the material is different. Something is available here cheaper, something is available there. So we always have to work with them and come up with a tailored solution for them, like what would be the circular material for their specific use, for their specific site. Because it doesn't make sense to create a recipe and create material here in Finland and then ship all of it to Mexico. The idea here is to figure it out what is actually available locally in Mexico and use that as a resource. As in a typical lifestyle, typical style of a startup, any startup is no startup if there is not the right team. And we have an international team of experts. Fernando is also here on this call, who is the CEO. So we start from the right, and Henry is a structural engineer from France. I'm in the middle, as you can see from my video and the picture. They match. Then there is Maria, who is right now working also with material development and robotic code, and Wycliffe, who is on the extreme left. He's our mechanical engineer, so he's developing this kind of mechanical systems. So all in all, I think I didn't take a lot of time, but I tried to briefly explain what we are, why we do what we do, and how we do it. So if you have any questions, please feel free to ask. And I would like to thank you again for inviting me for this talk.
Yeah, thanks, Ashish. We already have a few in the chat. If those persons, if you want to ask them also aloud, feel free to do that. Okay, bring it on.
What percentage of alternative materials do you manage to incorporate into the cement? This is the question, right? So first question. So as I explained in the case of the paper pulp production, so the material which we came up for the wood manufacturer, that mix has no cement, has zero cement, 90% recycled material, only 10% which is not recycled is gypsum. But we are also working very hard to actually replace that 10% gypsum, so we can create like 100% recycled content. So in that specific case, no cement, but there are other cases where there is a certain percentage of cement. So let's say 10% to 15%, but we are again trying to reduce that. And the idea is to go over time and to try to actually replace completely. So like example of geopolymer. So geopolymer can be also based completely from blast furnace slag or some other material, and there wouldn't be any cement in that. So this is something which we are actively working on. Then the next question is...
Okay, thank you very much.
Next question is, how much faster or slower does concrete AM take compared to conventional concrete processing? So just to give you an example, so the project which I was talking, well, I briefly mentioned about the project in Mexico. So that project involves us creating 500 tons of concrete. So actually 3D printing 500 tons of concrete. And the client has given us an estimation of that this amount of work, because they built this kind of structures and this kind of plants everywhere around the world. So they have experience. So they have told us that it would take them 6 months to build this by traditional technique. And according to our calculations and according to our experience and according to our test, we think that we can do it in 3 to 4 months. So we can reduce that time by half. And according to the current calculations, it's going to be cheaper to do AM in concrete in Mexico than to use traditional technique in Mexico using the local laborers. So this is the answer to your question about the cost. But it doesn't make, well, cost makes only sense in certain cases, but in this specific case, it makes a lot of sense. And that's why the client is actually going through it at this kind of larger scale. Because I haven't met any client who says that, okay, AM is cool, it's expensive, but I want to do it because it's cool. Everybody wants to do it because it's safer, faster, and cheaper. So that is one of the main reasons why people are turning towards AM in concrete than the traditional technique. Just to give you an example, we can create a tall column of 3 meters. We can 3D print that from 10 minutes to 20 minutes. So AM in concrete is very fast. You can see some of the videos on our social media of Hyperion Robotics or social media of mine, and you can see how concrete 3D printing goes in real time. It's really fast. What is the project you're developing in Mexico? Yeah, well, so we are working with a Argentinian company which builds oil and gas plants around the world. Infrastructure, and they have a plant in Mexico where they need to do a lot of concrete infrastructure. So this is what we are doing, concrete infrastructure for them. How about stability of printed walls at larger dimensions? What is the largest size of aggregate that you use? So the largest size of aggregate which we use is, right now we have used 3 millimeter is the largest aggregate. So that's the largest dimension which we have used. But just to give an example, like normal concrete, which is, I'm sure, is everywhere around you, where you're sitting right now, has 25 megapascals of compressive strength. The 3D printed concrete has the one which we have, has compressive strength of 55 to 65 MPa, depending on the dimensions like X, Y, Z. So in certain direction, it has more 65 MPa, in certain directions 55. It's like more than twice compressive strength of traditional concrete. So next question, is the AM concrete itself recyclable again? Yes, it is, because in the end, it's concrete, right? So the one project which I didn't mention, which we are working also with together with Manchester Metropolitan University, that is also with a large, they also have a larger funding, which is called a Sprint City. So using recycled materials for different AM processes. And what we are doing is developing a concrete mix for them, where they are using construction waste as a replacement aggregate for normal aggregate, which is normally mined from the rivers or mined from hills and mountains. So there we are using recycled aggregate and creating a new recipe based on that. And concrete AM, as I said, it's not a different material, it's still concrete. So it can be crushed again and can be used again. There is nothing in it which is not in the current concrete. It's just that the recipe is different. The consistent of different raw materials is different.
Thank you, Ashish, for all the info. I have a question on the setup of the factories. Actually, on one slide you show like a really nice picture of a factory full of robots that move around and print stuff. I know that in many countries they're looking at that kind of factories, but do you also envision maybe that that actually the factory moves around from project to project, or do you see more a trend like existing companies who have big facilities where they produce prefab concrete and then transport it, that in those facilities just will roll in a lot of robots? Or will the plants be moving around from project to project and do things on site, limiting transport of heavy concrete structures? Sort of
yeah, this is actually the point. So Iberdrola, the Spanish company, the whole idea here is that we will go to the site. So wherever they have this kind of wind turbine installation, they have a small substation, and then there are like foundations there. So the idea is that we go to a site, 15 days, 1 month, depending on what is the scale of the project. We do the printing, we move to the next site, and we move to the next site, we move to the next site. The Argentinian clients also, the site is in Mexico, but they have projects around the world. So maybe the next site will be in Brazil, or next site would be somewhere else. We are also talking to another company in India, which is also an energy distribution network. So they have this kind of pylons, and as you have seen, like they can be anywhere in the world, right? So they can be in very remote locations, and that's where the AM makes more sense, because you can actually take the printer to the site, do the printing on site. The remote location also has problems of why the project in Mexico is cheaper. It's because you have to take all this labor to this remote site. You have to pay for their accommodation. You have to pay for their food. Also, the remote locations might not have laborers which are trained in making concrete. So there are like a lot of these restrictions, and that's why 3 of the projects out of the projects which we have is where the concrete printing will happen on site. Wherever the site is, and it will just move around. And that's why also the choice of robotic arm was there, because the robotic arm can fit on a Euro pallet, can be like shipped easily, can be installed very fast, and can be unmounted and uninstalled very fast. And that was the reason.
So basically, we could go to a scenario where you have a small construction yard and there's one robot printing concrete, another one is printing certain plastic parts, and then maybe the other one is doing some fiber composite printing. Could be a collaboration between different nice.
Yeah, exactly. So this is also our longer term vision, is that the construction site will have, as you explained, like many different type of robots, many different types of automation. You already have the robots from Boston Dynamics who can do the site surveying, 3D scanning, can tell you what is missing, what is not missing. And then they can actually provide instructions to other robots of, okay, this is missing, you have to go and build that. The robots which can lay bricks, they can do plasters, they can do painting. So all this, our vision here is that in the future, there will be like construction site will be full of robots. That's our vision.
Hi, Ashish. Thank you for the nice innovative projects and ideas. I want to ask you, have you ever checked the flammability of the paper pulp if there is any fire accident? So I suppose if it's used in construction, it can take destroy all the building's material if there is a fire.
The paper pulp is processed into lime materials, which is already the loss of ignition is the similar values as other construction materials like cement. So there's no issue on flammability. So don't imagine it is like really paper pulp, like paper pulp. It's processed into granular material, which has the same loss of ignition as other materials.
Okay, and I have another question. You already mentioned the strength of this paper material is 25 or around 65 megapascal. I don't know, is it really replaceable of concrete in terms of strength material if we use for high building construction?
Well, if you have higher building construction, then of course you need like more compressive strength concrete. So there are certain uses. So the paper pulp concrete has only 32 MPa. The other concrete which we have is 65 MPa. So this concrete can be used like in normal structures, but not for high rises. For example, for high rises you need products which can take higher compressive strength. So there we need to have another solution. But as I said, like all these solutions which we are developing are specific to what is needed by our clients. So if there is a need to develop something for high story structures, then we will develop it.
Okay, and one more question. I want to know the price of the robotics 3D printer. What's the price?
Yeah, that also depends on the use and the need. So cannot say that depending on, again, the use and the need, it can vary a lot.
Just as a general, is it a cheaper one or it's a very expensive? How I call it if just a knowledge just for, that's why I asked.
Well, it costs cheaper than to buy a house or to build a house. Let's say that would be answer. You can use that in any context in any country.
Okay, thank you. Thank you very much.
Philip, you had a question or?
Yes, so very impressive story, and also your experience. As you said, you used and abused every printer and the materials. I think the sugar approach is very interesting, and seems like you made a good success. But I think if you have such success, that somewhat must have been wrong at some point. So for our participants, they're also developing products now. What was your most memorable or most teaching mistake you made somewhere in the process? The most clogged printer? Or...
Well, the mistakes, like the whole advantage of startups is that we are supposed to be very nimble, right? And we are supposed to change very fast, and we are supposed to be like moving and shifting and changing your ideas. One interesting story is that when we started, the sustainability was really not the goal. The goal was automation. But we started realizing that that the whole construction industry is controlled by certain companies. And when you ask them like, hey, can you provide us 3D concrete printing material? They were like, maybe, who are you? I don't know, maybe not. And that created actually a necessity that we had to develop our own material, because these large companies just denied us access to their concrete 3D printing material or material which was available. And that created a necessity. So maybe it was not a negative point, but as I said, that we were not thinking of developing our own material. That was not the initial thought at all. None of us have experience in material development or concrete in our team. So that was something which came up to us, is like, hey, now we cannot get access to concrete 3D printing material. What do we do? Like, okay, we have to develop our own material. How do we do that? So I went and downloaded and read maybe 100, 200 research papers about concrete and concrete 3D printing, learned how to make concrete 3D printable, learned what is needed, learned what chemicals to buy, learned how to make it sustainable. And now, like, our core has changed. Like, now we also create our own material, and it's better in terms of sustainability than what materials are available to buy from other large companies. So this is something which was completely unexpected, as I said. So that was, let's say, for us, it put us back by a few months. We would have developed our technology and automation part better, but it also gave us this kind of new opportunity to explore. And now most of our clients are actually about sustainability and using end of life cycle products, and everybody's actually interested in that. So that also pivoted us in our startup and changed our direction in a different way. So it's always good. Like, this was a setback for us at that point, but now if I think about it, it was actually not a setback, but it was really good that those companies denied us access to their materials. So in that sense, it was positive. And yeah, we have made mistakes, but until now, so far, not many big mistakes. There are small mistakes which happen, but I think this is only example I can come up with, which actually was a positive example if you think about it.
Thank you very much. Very interesting story indeed. So I think Yannick also wrote a question in the chat for this regarding.
Yeah, okay. Yeah, Thomas already shared the link to the PhD. Fantastic. Yeah, great.
There is also the question Yannick has asked about not having any material experience was somehow an advantage, no bias. Yeah, that's actually like, yeah, because, you know, like when you talk to concrete experts, they always have this kind of bias towards the materials which they are going towards and the materials they have grew up with and have used it before. For me, it was like everything is new. So it's like I studied what is cement, what is blast furnace slag, what is silica, what is metakaolin, what is mining tailing, what is paper sludge, like what can I use and how can I use it? And I ordered samples of all the different materials possible and started just testing the recipes based on previous experiments which some scientists and researchers have done, combined some of those researchers together and like created like our own recipes and then tweaked them in order to make them 3D printable, because not all recipes were 3D printing recipes. Most of the recipes were experimentation of using some novel materials. So every recipe then we had to tweak to 3D printing recipe, and that was something which is still exciting, which we are still doing. So I'm still developing the paper pulp mix, because we want to increase the compressive strength. Geopolymer is still completely open. Right now we are at a stage that we have all the raw materials. So now next month after my PhD, it's going to be this kind of mixing of the materials and doing like scientific experiments of which one will actually work for us. So this is something which has still remained the same. Coming as a researcher, working as a researcher for last 10 years has remained the same. That in our company, basically we are doing research. So we are doing research and we are actually trying to commercialize that research in our company, trying to sell that as a product to our clients. And this is something which is very exciting.
And I think it's very nice that what you explained, that investigative look and that eager to develop things. It's something, a message we also, yeah, I try to convey, or we at the program where I teach, what we try to convey to our students. Not being an expert in something is not an excuse. You become an expert by doing, by experimenting, by testing, by just taking away the shells, the things that obstruct you. So yeah, really nice to hear, very inspiring. Thank you.
Yeah, like 6 months ago, none of us knew, well, we had some idea what concrete is, but really how to make concrete, none of us knew from our team. And now we have developed, I don't know, maybe like 20 different recipes which worked with 3D printing concrete. And this is something which we have developed together, and like which we have been working, and like this is something which is which also is very exciting for all of us now. How exactly is the next question I'll go to? How exactly is the process of selecting the right material for the concrete? Well, how the process of selecting the right material is very well. I will give you just example of Finland. So in the beginning, I was very excited about fly ash. I was like, fly ash is the best material. I want to use it. And then I figured out like you cannot get fly ash in Finland. It's impossible. And then the only way I can get fly ash is from China or from Russia or from India. If I want it in larger quantity, and that was already a no for me. It's like, why would I use a circular material where I have to get it from like halfway across the world? Then I found out that in Finland, blast furnace slag and silica fume are commercial products which you can just buy off the shelf. And then, okay, so that was the reason we started using blast furnace slag and silica fume, because it was available. I could order it and I get it in 2 days, 3 days, and I can work with it, and it was available. And the same goes where it would be somewhere else. If we are, for example, in Poland, fly ash is available. So if it was in Poland and if silica fume is not available, then the choice of material for replacing cement in Poland will be fly ash, or in India will be fly ash, because it's readily, very abundantly available. So the choice of material really depends on geographic locations and where the material is actually available, and where is the problem, like where is the problem of that material in that sense. All right.
Yeah, do we have more questions coming up?
Have you tried to expose the aggregate in your concrete to grind it, so you can have like pretty beautiful surfaces when you grind it a little bit to expose the aggregate and then polish it?
No. But okay, also it comes from my background. That's another reason. So in my internship as an architect, I worked with an architect who used to work with Le Corbusier. So it's who came up with the whole pattern route, you know, like patterns. And for my internship, for 1 year almost, I was doing those shuttering patterns as my internship. So I was drawing them in CAD, that this is where the wood shuttering will go. So like I am very biased of like how the process leaves its mark on the object which is created. So the same goes for my PhD. So the whole PhD is all about the process is the master. So the process and the process, how he leaves the mark on that surface or on the object. And in that way, I'm very purist. So the way the concrete is 3D printed and the way you see the layers, as you can see in this picture, this for me is pure beauty, like for concrete.
It does sound.
This is a pure bias.
Nice. Yeah, I was just thinking that I didn't mean to grind it like to fully flat, but to still have the layers. But I mean, then the top of the layers would have exposed aggregates, and they might have like a polish. So then you would also have in the grooves the rough surface, but then the tops of those layers would be polished, for an example.
Yeah, if a client wants it, we'll explore it. So right now also like lots of our development is also driven by the clients. We also have our own internal projects and our own internal research, but a lot of projects are governed by what the clients want.
Ashish, maybe a question to you then, as I found interesting what you said so your background as an architect, your reference to Le Corbusier. In your opinion, do you see a new digital age in architecture coming up? Will robotic manufacturing redefine the buildings around us, or do you think architects will use it and expose it, show it, or will it be something hidden? Will it be
Well, that question is gonna get some controversial answer from me.
Yeah, go for it. Go for it. Go for that. Go for it.
So, well, okay. As I said, like my first statement was that I'm very much interested and passionate about how technology influences the way we build, right? So when we have the whole industrial age and we started building with steel, you know, like we started building with steel. When we started building with steel, we started creating new type of structures. The spans were larger. You could see the difference between like how a building is built in wood, how a building is built in concrete, and how a building is built in steel. Like one of my professors always used to give examples like, how do you take advantage of steel as a material if you want to create a column and a beam? So if you're doing a column and a beam, so this is the column and this is the beam. In wood, you will do it like this. In stone, you will do it like this. But in steel, you can do this because you can weld steel, right? And that gives you complete different potential and what you can do with steel. The same with concrete and and the same with additive manufacturing. So with additive manufacturing, you can do new type of buildings, you can do new type of architecture, you can completely redefine the way we design. Like also what we talk about in 3D printing itself, like design for additive manufacturing. Additive manufacturing can change the way things are built and the way they look like, because this is possible, which was not possible before. And all the examples of the buildings which you see, which are 3D printed by concrete right now, they could be also done with stone or wood, or like could be casted by concrete. Like they do not take advantage of the technology, so to speak, and they're not true to the technology. They're not using the potential of the technology. And this is something has to change if you want to come up with this kind of a new architecture or new worldview using AM, is that the thinking has to change, right? Like the thinking of how you make things have to change, and thinking of how you can take complete advantage of the technology has to change. And that is right now what is not happening. And like, I think if we get an opportunity, we will be able to do that. This is what I believe. But yeah, it's a controversial statement.
No, I cheer for you. Go for it. That's also, yeah. I think we are more active in product design from UGent, and it's also what we see. We see a lot of 3D printing being used in everyday life, just which can be milled or which can be made with any conventional technique, but people are not appreciating the textures, the shapes, and so on. So we need quite a cultural shift to. But it's nice that you help pave the way for AM. I personally think so. Good job. Cool.
Okay, if we still have some questions for Ashish, or okay, maybe something in the chat.
Have you done any experiments with hybrid material by mixing paper or cement or any other combination? I'm not sure if I understand the question, because concrete itself is a composite. So it's always using different materials. There is binder and there is aggregate. And aggregate can be anything, you know, like aggregate can be waste from rubber tires, for example. And we also have aggregate from recycled glass, like which is expanded glass. So it's a waste aggregate. We also have aggregate which is from waste building construction site. So we have done a lot of experiments. As I said, like we have a bunch of recipes using bunch of different ingredients from different industries and different waste streams, but they have to work together. So it's again like the question of binder and aggregate. So the aggregate and binder has to bind together and create like a cohesive composite material. If it doesn't do that, then it doesn't work as a material. So anything which works in the binder aggregate combination would work. So same like example in plastic 3D printing is that you have wood dust and sawdust, and you have metal powders which are always infused with plastic. So it works because it's infused, and it works in that way. So the same goes for concrete, like whatever combination could work as this kind of aggregate binder relationship and work together would work.
Okay, I think we are kind of getting close to the end of this keynote, and thank you, Ashish, very much for joining us, and especially I liked also the final, almost the lyric